Welcome to Malleable Matter. My name is Maria Jeanson and I'm the Strategy Manager at Imperial Tech Foresight. I will be your host for this afternoon. We have an exciting event ahead of us. There are 3 academics waiting to share their research today. If you're logging in from the UK, the session will run till midday. So this is the last of a series of 3 sessions for Tech Foresight 2014, exploring the theme of intentional creations. It is a virtual conference where we have looked at how we can reframe technology and scientific breakthroughs for good and create a course for positive technological futures. As Imperial College London, this is close to our hearts as we constantly work towards applying scientific discovery for the benefit of society. In this session, we have explored and will explore the future through the lens of cutting-edge research insights from world-leading academics across the college. The virtual conference started 2 weeks ago with meta-motivations. Last week, we covered moral machines, and today we will look at malleable matter. It has been a broad theme, and we have covered areas such as self-governing AI, building frugal sensing technologies, to biodiversity resilience. This is the last Thursday of the event, and we have been excited to inspire you and others to think differently about the future. The event has been brought to you by Imperial Business Partners, a bespoke executive platform for global industry clients who want to have an accelerated access to Imperial College London and our visionary ecosystem of startups, academics, students, and facilities. As a platform, it gives clients a unique approach to problem solving for research-driven industries, creating access to leading expertise, talent, and facilities, as well as insights like today. But for today, it's all about malleable matter. And in this session, we will explore how new materials can disrupt industries, from energy to wearables to automotive to architecture. What if our clothes could charge our phones? What if batteries were safe and completely recyclable? What if our materials became stronger to mitigate against impact? What if we could actually program them to behave like biology? Advanced materials and new developments could be the answers to these questions. Malleable matter might be the future. Today, we'll explore how material science could unleash a new wave of positive disruption, creating a better tomorrow. So enough of me. I want to introduce you to the first speaker of the day. Dr. Ulla Hekselman is a Faraday Institution Entrepreneurial Fellow in the Department of Materials here at Imperial College London. She's the co-founder of Solvatech, a startup leading the commercialization of green technology for lead recovery from used batteries. Her research goes beyond this, and today she will share her future vision of the battery revolution, where new material science can be combined with ethics and sustainability. I would now like to pass you on to Ulla Hekselman.
Good morning again, everyone. Thank you, Maria, for your kind introduction. It's a real pleasure to be here. As you said already, indeed, I'm an entrepreneurial fellow at Imperial College London, and I'm also a co-founder and the CEO of Solvatech, an Imperial spin-out company that is focused on battery recycling. But first and foremost, I am a battery scientist. My journey started in the late 2000s, just when the first Tesla Roadster and iPhone 3G were launched. I was then completing my master's project on electrolyte materials for lithium-ion batteries. These were very exciting times for battery researchers, and I personally wanted to be part of this rapidly evolving field. Fast forward to 2020, yesterday's future is today's present. Lithium-ion batteries are part of our everyday life, and today we have over 170 models of electric vehicles available on the market. At this point in time, we anticipate that the next technological milestones will include charging batteries within seconds, driving our electric vehicles for over 1,000 miles, and flying electric cars. And for myself, I continued pursuing an academic career and worked with some truly visionary scientists at the forefront of battery technology. However, while conducting fundamental research, it can be very exciting. It is not uncommon to lose sight of the bigger picture. The demand for lithium-ion batteries is growing exponentially. But Where are the raw materials coming from? What is the product's impact on the economy, environment, and on society? Is all of this sustainable? Mining, processing, and recycling of battery materials in a sustainable way is critical for our ability to scale without on our planet and society. I felt it was time for me to broaden the scope of my research, and I became increasingly interested in the entire ecosystem of lithium-ion batteries. Specifically, I was curious to learn how spent batteries are being handled at their end of life. Until recently, recycling of lithium-ion was virtually non-existent. There were no major recycling plants and hardly any scientific research. The R&D was purely about making the batteries cheaper, lighter, and more efficient. Considering how lithium-ion has become so widespread and popular, I was surprised to learn that very little effort has been directed towards solving lithium-ion end-of-life issues. So about 2 years ago, I started looking for comparable examples of battery recycling, and I came across lead-acid batteries. These would be your typical 12-volt batteries, which can be found in every internal combustion engine car. Interestingly enough, not many people would know that lead-acid batteries are also used in every state-of-the-art hybrid and electric vehicle. Unlike with lithium-ion batteries, there is not much hype around lead-acid technology, mainly because it's been on the market for about a century. What is remarkable about this technology, however, is that 99% of these batteries are being collected and recycled at their end of life. In addition, all components of lead-acid batteries can be recycled and reused in a new battery. Did you know that 80% of your new car battery is made of recycled materials? This is outstanding, not only when compared to other battery technologies, but also in comparison to any other recyclable product. Their recycling rates exceed those of paper, glass, or aluminum cans, making lead-acid batteries the most recycled consumer product in the world. This is thanks to various factors: the infinite recyclability of lead, the cost of raw materials, the simplicity of the product, and the enforcement of environmental regulation. This market is considered a perfect example for circular economy, but it is not free from issues and challenges. We all know that lead is highly toxic. Exposure to lead affects all organs in the body and often causes irreversible health issues. Long-term exposure to lead can be associated with cognitive impairment, behavioral problems, lower IQ, increased societal violence, and lower life expectancy. Today, human exposure to lead comes primarily from informal recycling of lead-acid batteries in low and middle-income countries. And it is estimated that up to 30% of children around the world might be suffering from lead poisoning. For that reason, informal lead recycling is considered the most polluting industrial process in the world. The existing method of recycling of lead-acid batteries includes crushing, separation of materials, and smelting. Smelting is a high-temperature combustion process done at 1100 centigrade, and it is the most energy-intensive and polluting step in the whole recycling process. It is also the most expensive step, because if it's done properly, it may cost companies up to 40% of their annual expenditure just to comply with environmental regulations. At present, there is no industrial recycling process on the market that is both cheap and environmentally friendly. With that in mind, my colleagues and I have developed an alternative method to smelting. We do not reinvent the wheel, so to speak, but rather take out the most expensive, the most energy intensive, and the most polluting part of the process, and we replace it with our low temperature solvent-based technology. This new method allows recyclers to avoid the smelting step. In its essence, our patent-protected technology is using a special type of solvents, called dipotectic solvents. We use them to recover lead from used lead acid batteries. Dipotectic solvents are composed of low cost, easily available, and benign chemicals, such as ethylene glycol. They have a low environmental impact and are easy and safe to handle. Most importantly, they have the ability to dissolve a wide range of lead compounds, including components of used lead acid batteries, which are otherwise difficult to dissolve, or are even insoluble in other liquid media. Our process is solvent-based, so we produce significantly less hazardous air pollutants during the process. We also significantly reduce CO2 emissions, which together makes lead recycling more environmentally friendly. We also move from smelting at 1100 degrees to temperatures as low as room temperature, which reduces energy consumption and makes the entire process much cheaper than smelting. Finally, we are also faster because we require fewer steps to produce lead products that can be used in new lead acid batteries. As I said, there is no lead recycling process on the market that is both cheap and environmentally friendly. But our technology has potential to address this environmental, societal, and economic issue. To fully maximize impact of our research at Imperial, my colleagues and I decided to set up Solvatech, a spin-out company dedicated to the commercialization of this technology. We work very closely with established industrial partners, recycling experts, and our future customers to meet commercial requirements. And this is a very exciting part of the journey for our team because it gives us an opportunity to look at our process beyond the laboratory scale. We analyze the economics of our process, or we develop the solvent recovery system to minimize the production of chemical waste. Currently, the technology is at the prototyping stage, and once the model is proven at industrial scale, the technology will be deployed worldwide. And while this is already greatly exciting, the future is even more interesting. It is widely recognized that climate change is the most serious and threatening global environmental problem. One of the ways this challenge can be addressed is by transition to a carbon neutral economy. And an increasing number of countries and organizations are already targeting net zero emissions by 2050 or even earlier. From a wider economy perspective, this can be done, for example, by moving away from fossil fuels to electricity generated from renewable energy sources, such as wind, hydropower, or biomass. Another option is reduction of greenhouse emissions generated by our transport system. EVs are a great option for reducing our carbon footprint in comparison to standard petrol or diesel engines. Electric vehicles market grows steadily in the last few years, reaching sales of 2.5 million units in 2019, which is slightly less than 3% of total vehicle sales. However, the real takeoff for EVs is expected to happen from the second half of the 2020s, when electric cars are expected to become cheaper to own than internal combustion engine models. The electric vehicle revolution is responsible for surging battery demand. Today, the size of lithium-ion market is driven by expansion of the plug-in hybrid and electric vehicle market. The increasing demand for lithium-ion cells is met with an increasing number of gigafactories, which are built around the world. Once the battery market moved to the economy of scale, we started to observe the drop in battery prices. This, as a result, makes the electric vehicles more affordable, which then further increases demand for batteries. This spectacular success of batteries and electric vehicles is expected to continue for the next 2 decades. This unprecedented demand can be only compared with the demand for oil in the 1910s and 1920s. One could ask then if batteries are the new oil. However, this success also puts an enormous strain on the entire supply chain. To meet this demand, we will need to produce more and more batteries. but we only have a finite amount of resources. If we continue expansion at this speed, we will soon run out of raw materials such as lithium or cobalt. Therefore, the real question here should be, are batteries the new oil or the new plastic? The answer to this question is around sustainability. We have to build our sustainability map for lithium-ion batteries, and we have to build it now. And we all have a role to play here, starting from us, material scientists, engineers, car manufacturers, regulators, all the way to all of us consumers. We can contribute to making batteries more sustainable. For the last few minutes, I will share with you how we material scientists address this problem. First and foremost, we shall make our batteries safer, more efficient, and last longer. For the first example, I've chosen a material that is responsible for making battery headlines in the last few weeks. It is a cathode material called NMC, which stands for lithium manganese cobalt oxide. These materials have a layered crystal structure, which allows a facile intercalation and deintercalation of lithium ions upon charge and discharge of the battery. The original layered material here was lithium cobalt oxide, and it was successfully used early on in small portable electronics. However, cobalt is more expensive and less abundant than other transition metals. Cobalt also presents political and ethical issues because of the way it is mined in Congo. As a result, cheaper cathodes have been developed to substitute some of the cobalt with nickel and manganese. These are used in the majority of lithium-ion batteries in electric vehicles. And it's done due to their high specific capacity, ease of production, and moderate cost. The material I want to mention to you is NMC 532, where 5, 3, and 2 corresponds to atomic ratios between nickel, manganese, and cobalt. It was produced as a single crystal, unlike other cathode materials, which are typically polycrystalline. This made NMC 532 extremely resistant to oxygen loss from the crystal structure, and as a result, lithium-ion cells with NMC 532 have an exceptional performance in terms of cycle life. These new batteries would last for over 16 years and over 1 million miles. This work was done by Professor Jeff Dunn and his group from Dalhousie University in Canada. Jeff is also known for his close collaboration with Tesla, which announced that they will be implementing a game-changing battery technology later this year. Another example of making batteries more sustainable would be solid-state batteries. In that case, an organic flammable electrolyte and graphite-based anode would be replaced with a ceramic electrolyte and a lithium metal anode. This would increase the range of the battery and address the safety concerns. Currently, research efforts are focused on discovery of the most suitable electrolytes that will be mechanically and chemically stable with lithium metal. And they will provide intimate contact with the active cathode material upon charge and discharge. But actually, I'm not sure if it's changing. Okay, great. But actually, there is already a battery technology on the market that works with metallic lithium. This is lithium sulfur battery, where an anode is made of lithium and a cathode comprises elemental sulfur. Both lithium and sulfur are extremely light materials, delivering high energy batteries. This is suitable for applications where weight is critical, for example, aerospace. Moreover, sulfur costs approximately $200 per ton, which is much cheaper than cobalt, for example. It is also much safer to work with, and there are no heavy elements involved, which positions this technology strongly on the sustainability scale. Then, we also have to look beyond lithium and lithium ion. And there is currently a lot of work done towards new chemistries, such as sodium ion or magnesium ion, where materials are cheaper and more abundant. And of course, the sustainable recycling of batteries at their end of life. However, this is extremely difficult to establish at this point in time. We have a large number of different chemistries on the market. Elemental composition of batteries varies greatly, and there is no sufficient legislation in place to determine manufacturing standards, collection, or recycling. But for the time being, the clues are in the cost of lithium cells. What are the most valuable components? From this breakdown, one can see that over 50% of battery value is in its cathode materials: nickel, lithium, cobalt, and manganese. Not surprisingly, the most advanced method of lithium-ion recycling today is pyrometallurgy, where batteries are smelted, and they produce alloys of copper, cobalt, iron, and nickel. The slag from this process typically contains aluminium, manganese, and lithium, which can be reclaimed by further hydrometallurgical process. But electrolytes, plastic, and lithium salts are usually lost in the process. Despite environmental drawbacks, high energy costs, and the limited number of materials reclaimed during pyrometallurgy, this is a frequently used process to reclaim high-value transition metals such as cobalt or nickel. Hydrometallurgy involves the use of aqueous solution to leach metals from cathode materials, typically sulfuric acid and hydrogen peroxide. Subsequently, metals go through precipitation reactions to recover cobalt and lithium, or transition metals, or NMC. The big issues to be addressed with all hydrometallurgical processes are the volumes of solvent required, the speed of delamination, the cost of neutralization, and the likelihood of cross-contamination of materials. And direct recycling involves removal of cathode or anode material from used battery, followed by reconditioning and reuse in a remanufactured battery. For example, after dismantling used batteries, cathode strips could be delaminated in a solvent, powders could be recovered and regenerated, and lithium content could be replenished and compensated for losses during battery use. And finally, bioleaching. It's a method in which bacteria are harnessed to recover valuable metals, such as cobalt or nickel. This is a relatively new method, but has been successfully used in the mining industry. And it can be potentially complementary to pyro and hydrometallurgical processes. On this slide, I just want to share with you work published recently in Nature Energy, where dipotectic solvents were used to successfully recover lithium cobalt oxide from used lithium-ion batteries, with efficiencies as high as 99%. Similarly to our work with lead acid, they also showed that it is possible to recover and reuse the solvents. So how will the sustainable battery market will look in 2040? EVs will make up the majority of new car sales worldwide, but we shall be prepared to be using air taxis by then. For every terafactory, there will be a terra recycling plant. Our batteries will be made from recycled materials, and if it's not possible, from materials that will be ethically sourced. We will have a range of battery technologies with their chemistries optimized for different applications, whether it is transport, stationary energy storage, or wearable electronics. The battery cells, packs, and modules will be designed to enable efficient disassembly, separation of components, and material recovery. Legislation-wise, there will be strict regulations about who is responsible for battery recycling. New ownership models will be in place. For example, we may only lease the EV battery pack from a car manufacturer, and they will determine whether the batteries will be repurposed at the end of life or recycled. And finally, coming back to lead recycling. I hope our technology will become a global standard for lead recycling, and we will eliminate lead pollution. Because it doesn't matter whether it is 30% or 0.3%, no children should be suffering from lead poisoning. Hopefully, this talk highlighted for you how important sustainability in energy storage is. Either these are lead acid or lithium-ion batteries. And what are the risks for not preparing for it? At the end of the day, it is our responsibility, either as academics or Imperial business partners, to build a better world after the COVID-19 crisis. A world that is cleaner, more sustainable, more energy efficient, and more respectful of the climate. Thank you very much.
Thank you so much for your talk. It was really insightful. I especially thought it was interesting to hear how we might in the future even share the way we see the ownership around batteries. So putting more of a responsibility perhaps on the car manufacturers. So I have a couple of questions that have come in from the audience ahead of this event. So the first one is, can we envisage the solvent-based recycling technology to be adopted to the point of use? For example, could we see battery recycling or refurbishment being done in high street shops, or maybe by consumers themselves?
Oh, wow. I'm a chemist, so my first answer will be, don't try this at home. But so actually the solvents that we are using, they're really benign. They're not dangerous. Some of the components are used as food additives. So I'm not concerned about this too much, but batteries themselves, either lead acid batteries or lithium-ion batteries, they are made of toxic materials. And definitely nobody who's not qualified shall not try to play with it. They're also dangerous because, especially with lithium-ion batteries, what's encapsulated inside are volatile, organic, flammable solvents. So we really have to be careful. However, I do kind of get the point of trying to distribute points of recycling. At the moment, especially for, I can speak about lead acid recycling, it's dominated by economy of scale. So there are very few recycling plants. So for example, in the US, there are only 7 recycling plants in the entire country. So imagine about all these used lead acid batteries traveling by car to those recycling points. There is some good thinking in this, I agree.
Fantastic. And there's a question that's come in from the audience today that's a little bit connected to this. So what do you anticipate being the biggest challenge in getting battery recyclers to ditch smelting and move to Solvatech instead? Do you think there will be much inertia to overcome?
It's interesting. I think it will be regulations. So we have constantly tightening environmental regulations, and that's for good reasons. And if I have to say, there are several companies that are interested in changing to green solutions. If it's possible, obviously we have to prove they're economic, they're economical. But if companies have choice, you have people behind companies and they do care about the environment, they do want to do the right thing. And especially, and this supported with regulations, I think there is a change coming.
So do you think so what do you think is the biggest challenge at the moment for them moving to Solvatech instead? Is that changing the complete?
I think we're just too small and we're not ready yet. If we were ready tomorrow, that would be great. But we're a small startup, so trying to grow slowly. But actually for lithium-ion market, it's legislation and there is still no clarity what happens with used lead acid lithium-ion batteries, what happens with the batteries from our phones. And then very shortly we'll have an issue with all the batteries coming from electric vehicles. So we have to address it now.
Fantastic. And Nick Rimmer has asked, does Solvatech have a solution for lithium-ion batteries today? I know you shared a little bit of research at the end. Can you share a little bit more?
We are working on this, and that's definitely the next thing that we're going to be involved. And we are, I'm Faraday Institution Entrepreneurial Fellow, and Faraday Institution is the biggest funding body for funding energy storage research in the UK, and we are strong on this. There is a strong recycling project going on, so if you want to check it out, please go online and look it up.
Fantastic, and it's almost like watch this space with Solvatech as well then.
Absolutely, please do.
So another question from James here is there a standard or potential basis for one which could be made law, which should be used or met for batteries in the circular economy?
Oh, so there are so many, it's difficult. There is no one, there are European Union regulations. So it's end of life directive for batteries that is being revised now, and European Union is trying to capture all different technologies in there. So hopefully there will be standards. There will be also local standards, probably our own standards in the UK. And then the market itself, I know about companies that are outside European Union, but their business partners are in EU, so they want to comply with these regulations. So they follow them, even though they're not required.
Do you think there is room for better laws and regulation then around circular economy, especially in concerns to batteries?
Totally, because there is no regulations on lithium-ion. I think us as consumers, we really have to start thinking, where is this battery coming from? What happens with it when I change my phone and I ditch the old? Something that we may not, so I didn't mention the supply chain, but for example, problem with cobalt is that it might, having a phone, we might have somehow indirectly contributed to child labor, because the cobalt mostly comes from Democratic Republic of Congo. And then at the end, do we know what happens with our batteries? Are they probably, our electronic waste is probably shipped somewhere in Asia. And we are a polluting industry, even though on a daily basis, this is not something we would do, but we might unknowingly contribute to the problem.
And I guess it's something that was made even more clear after the COVID crisis as well, around supply chains and making it all in countries that are like trying to think about ways to decentralize both recycling, but also access to batteries.
So I can, so also I didn't have time to speak about supply chain, but at the moment lithium is coming, for example, from Chile, nickel is coming from Australia, and cobalt is coming from DRC. And they all go to China, where the lithium-ion cells are produced, then it goes to Korea, where the car is produced, and then it goes to the US or to Europe. And just by the time you receive the keys to your electric vehicles, imagine the carbon footprint of this. But there are changes in the market all over the world, and also in the European Union, and especially there is more focus on this. There are things happening, and they're happening really fast, and I'm really happy. So I look forward to those changes and having more transparency and regulations. And I think even at this point, European Union is considering passports for the materials to actually know where they're coming from and where they're going. So that's something to look out for.
That's really interesting, with an increased transparency of materials as well. So I think we'll do one more question, which I'm actually quite keen on understanding a little bit more as well, which is another one from Nick Rimmer, who asks, why haven't lithium sulfur batteries been more successful? They sounded very promising from your talk.
Yes. I was thinking about it again the other day. I was like, oh, well, actually, not recyclability, their life cycle is not as good as for lithium ion. So their life cycle is much shorter. So maybe not 1,000, 2,000 charge and discharged cycles are available. So they're really good for shorter use, but for very specific applications. But also in that space, there is a lot of research going on, and there are companies that are looking into it. And batteries are a very dynamic field, for sure.
Fantastic. Thank you so much for sharing your vision on the battery technologies and the future of the work that you're doing with Solvatech. these were the questions we had time for now. Audience, remember to continue to send in questions into the Q&A field. We'll be able to answer some of them in the roundtable discussion at the end of the session. Another expert in advanced materials is Dr. Felice Torrisi, he's a lecturer in 2D materials and wearable bioelectronics in the Department of Chemistry here at Imperial College London, and leads the group Wearable Electronics with 2D Materials, with a particular focus on energy, sensing, wearable electronics, and bioelectronics. Today, he will share his vision on the future of wearables and how a new humble material might get smarter. I now want to hand you over to Dr. Felice Torrisi, who will share his vision for the next era of wearables.
Thank you, Maria, for the introduction. I'm going to share my presentation. I hope you can see that. Yeah, so indeed, today I'm going to present a new idea to enable really a step forward in the area of wearable electronics. And the idea, of course, is to start from what we think of wearables nowadays. So we always think of wearables as gimmicks, for example, that they are similar to watches. We can wear them around our wrist, and they are good at measuring some of our body properties, for example, the heart rate. Of course, you can get, for example, number of steps you have been running on a day. However, statistics shows that normally people get bored with these type of devices like Fitbit or watches after a couple of weeks. Actually, there are statistics from Gartner showing that after 6 months, people tend to actually stop using these devices simply because they are limited in what they can do, and also they're not really reliable. And eventually, actually, the key problem is that they're not truly wearable. So if we look instead at what wearable devices are nowadays, they are similar to watches, most of them. And we can define them really as essentially the standard rigid electronics miniaturized and combined into a mix of interconnections, sensors, light-emitting devices, transistors. But the key problem in limiting this technology from actually being really upscaled and also really hosted in several other wearable devices or wearable elements like clothes is the fact that they are definitely not breathable and neither stretchable. So the key problem there to enable, of course, these devices to be more incorporated is to start tackling those issues. So what if we could actually make devices that are, for example, really conformable to our body? So we can think, for example, at elements or electronic components that really take the shape of our body. For example, if you look at the image there, you can see a truly wearable glove that, for example, could teach us how to play piano. Or what if we could think of devices that actually are directly interconnected to our clothes, and they could, for example, provide us information as we move around in a new city, or even more importantly, reliably monitoring our body parameters and giving us information on our health state. Bear in mind that this becomes extremely important in a post-pandemic setting like the one we are living now. Actually, we're still living the pandemic, but it will become even more important afterwards, when you would really like to keep vulnerable patients outside hospitals while still keep monitoring their body parameters. And this has to be done, of course, in a reliable way. So the research in this field, in my case, really started by looking at the wearable computer concept in the 50s. So the left-hand side image shows what they meant by that. Essentially, it was a miniaturized television that you can wear like a pair of goggles with a couple of antennas. And it was nothing but essentially showing TV channels, but it could be worn on a sort of shape of glasses. So of course, if we move towards 2020, we have improved a little bit of technology, but still we call wearables, or we think we are the forefront of wearables when we combine wearable garments or like gloves together with rigid electronics or metallic wires or interconnections, and these are connected to batteries. So therefore, of course, I wouldn't really call all these systems wearables, and particularly they could be hardly integrated with our current clothes. So if we need to enable really wearable devices, we need them to really look like something that we want to put on our body for a long time. So definitely they need to be stretchable. Stretchability is a key element because of course you want your garments or your wearable devices to conform to the stretch of our skin, for example, and being really comfortable over time. Of course, if you want to wear them for a long time, they need to be low power. So power is really important. So designing simple and low power devices that could be integrated and stretchable, it's key in this technology. Conformability links up to stretchability, but particularly the ability to really follow the shapes and the changing shapes of the body. Breathability is very important, particularly looking at devices that need to stay in contact with our skin for a longer time to avoid, for example, inflammation or developing, of course, skin diseases. They need to be easy to integrate with clothes, simply because clothes are the garments, the element that the item that we wear regularly every day. So of course, if you want to make things wearable, the way forward is actually to improve weavability. So integration by weaving, for example, with clothes, or somehow patching, for example, with the existing clothes. And last but not least, washability. Because of course, this links up also to the fact that you can reuse the devices many times. So if you can enable these wearable systems to be washable, or at least water resistant, you can wash them together with your clothes and you can reuse them several times. To do that, the current technology is not feasible. So we need new materials, and that's what I started looking into more recently. So of course, I focus on textile because essentially we already know that textile for wearables, it's an ideal material. It ticks all the boxes of the requirements I showed you before. It is breathable, it is highly stretchable, it's washable, and also it conforms well to our skin. Indeed, we keep wearing and we wear it regularly. So of course, textile is a great starting substrate. And we know that textiles can be also modified, for example, using standard dyeing processes. The fact is that, of course, these dyeing processes mostly rely with solution-based approaches, of course, at least water. And also we need to consider that these fabrics need to be washable as well. So I start looking at new materials that can help me in actually tackling this point, while, for example, providing functional properties that go beyond, for example, pigment or color. So of course, I started investigating a material that I'm very familiar with. I've been working 12 years on graphene and 2D materials. So graphene, we know it very well, particularly since 2010, where it won the Nobel Prize, and then the huge investments from the European Union on the graphene flagship project, trying to really move this technology from the lab into the market. Graphene, by definition, is a 2D material. So it's an atomically thin material made of carbon, and it's got an arrangement that looks like a honeycomb shape, honeycomb-like, and essentially being very thin and also biocompatible, it's actually very suitable as a material to enable smart electronic functions. Indeed, it's got many positive features for wearable electronics. It is definitely very transparent, being very thin. It is conducting. It's actually quite stretchable, up to 25% stretchability. It is environmentally stable. There's been a lot of results over the couple of years really showing biocompatibility of these devices and this material. So this becomes really extremely important element to enable truly wearable devices. And the good thing of graphene is that it really leads a family of 2D materials that can be extracted, for example, from layered materials by various processes. I've been leading, for example, research into solution-based approach to do that. And these materials offer different properties, different electronic and optoelectronic properties that are mostly complementary to graphene. So if you can consider graphene as, for example, your electrode, these 2D materials could be semiconductors or insulators. So essentially, they're really a good platform for wearable electronics. And this has already been demonstrated with devices going from touchpad, for example, to haptic interfaces, to energy storage elements or supercapacitors using graphene as electrodes, even to, for example, light emitting devices or optoelectronic devices. And you can imagine that all these devices enabled already with these materials on a non-conformal and flexible substrates have been already the basis for example, new types of health trackers and also well-being devices. So there is really a key promise there. However, if we want to integrate these into textiles, we need to make inks and dispersions. And that's where really my research has been leading this field, because I looked at exfoliating, for example, 2D materials starting from layered materials, either in solution, using, for example, shear forces generated by various processes, starting from the simple ultrasonic processes to a very complex and high yield microfluidization process that allows us to get up to 10 liters per day. So you have very large production of graphene inks, and these graphene inks are highly loaded of 2D materials, for example, and it could be, of course, used to make electronic devices, for example, through printing. As I said, this concept is very general. It could be extended to the family of layered materials, and indeed, you can come up with a large range of inks made with these 2D materials. Again, bringing over the same properties that they had at the origin, so semiconducting, insulating, and electrically conducting properties. So these then become a key platform for a new range of printed electronics that can enable truly wearable and electronic textiles. This has already been demonstrated, for example, to enable flexible organic light emitting devices or flexible printed transistors, or even, for example, touchscreen and even smart windows. So my idea is to see whether these inks can actually be incorporated into textiles using already industrially scalable, industrially relevant printing processes on a fabric, like, for example, screen printing or inkjet printing. And this, of course, requires a technology that enables these devices to be deposited and adhesive to those substrates, to essentially make it washable. So I focus my attention on designing adhesion processes of graphene and 2D materials inks on a fabric in order to enable fully printed devices on various fabrics. So for example, you can look at this, for example, fully printed keyboards that actually resembles an integrated circuit. So you have pads, interconnections, battery slot, you have speakers, and then you have an interaction with a motherboard that actually controls the entire device. But at the same time, you can actually consider to directly print, for example, external communication devices like antennas, for example, waveguides. And this can be just enabled by graphene. So of course, I'm going to show you step by step how you can improve, of course, the functionality on fabric, including also the other 2D materials. So to improve the adhesion, I started looking at standard fabric, for example, cotton fabric, that is very well known, of course, in the wearable industry. And I tried to gently modify this fabric. This is a very common process, for example, done for dyeing, creating a thin layer of positive charges by a cationic modification. And then I took my graphene ink and I again modified in order to show negative charges. So as you can imagine here, negative charges and positive charges strongly attached to each other, strongly adhere to each other. So actually we have an electrostatic interaction that improves strongly the adhesion of, for example, our graphene ink on a standard fabric. Then I took my negatively charged graphene ink, and for example, I formulated for being printed by inkjet printing. So here you're looking at a single drop generated by an inkjet printer nozzle, and this carries a very consistent and controllable amount of graphene that you can deposit regularly, drop on demand on a substrate. So for example, this can enable graphene-coated fabrics. Here you can see a comparison between a white cotton fabric and a graphene cotton fabric. And then after an ironing process that is commonly used, for example, in textile, you can actually have a uniform and strongly adhering thin film on top of our fabric that looks at the cross section of the fabric. And here you can see actually at the top view, there is a thin coating on top of the fabric where you can actually see the cotton fibers underneath. So this is a key technology to improve, of course, the adhesion of the substrate and enabling, of course, washability. Indeed, these devices result washable up to 20 times with standard washing procedures with ISO standards. So this means that we can enable, for example, truly textile, actually in this case, cotton textile wearable devices. Initially, I started using this graphene cotton fabric as a motion sensor. For example, I start looking at the uniaxial and biaxial monitoring of the wrist position using, for example, strain, change, and compression. And this allows to have a constant and very robust way of monitoring the position of our wrist as a function of a change in resistance. But of course, this can be even further improved. We have an IP on this for using it as a pressure sensor. So that's a key point because, for example, it enables to make sleeves or parts of garments smart and actually interactive through, for example, a touchpad. But of course, we want to move beyond simple touch devices. So we start really looking at the opportunities for this new technology into ECG electrode and healthcare application. So we use, for example, these graphene textile electrodes and compare them with standard ECG electrodes. You might know ECG electrodes. They are rigid electrodes that normally are placed on top of the skin. They are made normally of silver chloride. And then what we did, we compared it with graphene textile electrodes. And surprisingly, but extremely importantly, we can actually extract exactly the same ECG signal that you would extract with silver chloride electrodes, with actually a resolution to spot out these PQRST peaks, typical of ECG and very important, for example, to the medical staff, with a big difference that these devices, the graphene electrodes, are actually stretchable, biocompatible, and washable, and they work at low resistance or low power consumption. This is also very important because around 20% of the patients actually can't undergo standard ECG because their skin gets irritated after long time exposure to the electrodes. So this really enables the extra percentage of patients to really get these treatments that they wouldn't get otherwise. We also want to go beyond standard electrodes. We really want to enable truly electronics on textile, removing any rigid component. And to do that, of course, we use scalable printing processes like inkjet printing, and we combine the true power of our platform of 2D materials. In this case, we printed polymer electrodes, and then a layer of boron nitride, which is an insulating 2D material, is actually a dielectric, and then a layer of graphene as an active channel. And we fully print a transistor directly on a fabric. And actually, a combination of these transistors enables integrated circuits directly on a textile, fully printed without rigid electronics in it. Here, for example, you can see a single combination of two transistors to form an inverter, which is actually a simple logic element of, for example, a microprocessor or a microcontroller. So you can see a lot of 1 and 0s here, and that really shows that these devices can be used actually to replace rigid electronics directly on textile. So here essentially you can imagine a piece of fabric with a little bit of printing that actually acts as an electronic circuit, and it does the job of it. Of course, as I said, biocompatibility is also very important, because if these devices need to sit on our skin, or even in the future being implanted into our body for a long time, they need to avoid being toxic and creating first inflammation. So initially we start looking at how neurons, for example, survive on a graphene surface. So here you can see a graphene electrode, and then a network actually of neurons that initially these were just single neuronal cells that actually create and replicate on top of the graphene substrate and create a network. So this type network actually allows them to talk to each other and to actually, of course, create synaptic interaction and, for example, activating information transfer. So this is a key result because it shows that graphene is not only an inert substrate, but actually promotes, of course, growth of biomaterial, biofilms in general. And more recently, similar results have been shown, for example, with myocardial cells and different types of also skin cells. So this definitely shows, together with other 2D materials, the potential also in bioelectronics and biocompatibility. And particularly, it opens up to devices, actually entire laboratories, that could be shrunk down into a piece of textile. And that's what we're working on at the moment. We're trying to design a smart patch, which is entirely made of textile and actually can incorporate on a cotton fabric an absorbing pad that, for example, take interstitial fluids or sweat, and it conveys towards an array of electrodes that perform multiple readings on different analytes, trying to discriminate, for example, concentration of different targeted molecules. This is extremely important because we can already print, of course, our transistor arrays on cotton fabric, and we can modulate and modify it to be selective to specific, for example, analytes. We have already done this for printed graphene field effect transistors for HIV and for HBV. And talking about viruses, you can understand how important this is as a wearable via sensors for new viruses. For example, in a pandemic period, you can think of integrating these printed devices, for example, on a fabric of a face mask and being able to monitor actually the presence of viral agents directly on the face mask. This is important, for example, for contact tracing, particularly on a post-pandemic period, when you really want to monitor the contagious and infection throughout the population. More interesting, we have worked more recently on a textile-based display. So this is a very recent work. We try to combine the graphene electrodes together with thermochromic elements. And actually by using printing technology and UV induction to actually cure our thermochromic ink, we're able actually to show specific images directly on a textile. And at the same time, we can use also our graphene electrodes to enable light emission by, for example, a combination of several 2D materials. The big advantage here is that we have a fast switching on a piece of textile. So this piece of textile can really work as a display with no rigid components with a very fast switching. So this, please really keep an eye on this because this is going to become a very important technology in the future. Indeed, in a short term, what I foresee could happen is definitely enabling light emitting fabric without standard rigid, for example, light emitting devices, enabling entirely textile-based displays or even textile-based sensors. For example, Google Project Jacquard is already thoroughly working into integrating sensors, touchpads, but I think that the incorporation of different technologies together can be enabled through, for example, 2D materials. This can bring, for example, to less screens and more integrated surfaces of large panels made of fabric. Also more intuitive interaction, improving our interface with the outer world, as well as, for example, extending the gaming experience, particularly for smart gloves or also smart vision. This becomes on the short term also important to create a so-called concept of body area network, more looking at, for example, healthcare applications, integrating power generators with sensors, different type of sensors that are, for example, interconnected via wireless type of devices. This can definitely improve, for example, the invisible monitoring, highly needed, as I said, to keep patients away from the hospital while keep monitoring them thoroughly when they're really vulnerable. And also, for example, tracking invisibly specific body parameters that are indicators, for example, for infections, for specific diseases being developed. And of course, in the mid-term range, I'm looking at more integrated and responsive devices that, for example, could also being more stretchable and integrated with our body. So for example, the idea of smart contact lenses or biopatches, they could be also implanted, for example, with the skin. Contact lenses have a true advantage of being directly in contact with body fluids. So you can use them not only, for example, for drug delivery, but also to improve our vision capabilities. For example, you can improve the night vision. You can extend the visible range of humans by improving the IR range and getting into, for example, night vision just by a contact lens. But at the same time, you can also think of adjusting the sight. And over a longer range, I see more and more becoming important the concept of bioelectronics. So the electronics, which is really interacting with our living electrodes, which, for example, are neurons, like, for example, integration of nanomaterials or nano machines, or for example, 2D materials directly into our body, not only for drug delivery, but also as a sensing elements, using, for example, wireless interconnection because of their, for example, resonance with light, resonance with specific terahertz, for example, wavelengths, as well as direct interaction of biocompatible electrodes and our tissues. For example, here you can see a project that we're working on at the moment where we're actually using biocompatible fibers that are in contact directly with the brain surface. This is the dura mater. So the dura mater is the inner part of our skull, and underneath that you have the crust of the brain. And if you can actually improve this interaction, that really leads to an intimate, very intimate contact of biocompatible elements made of 2D materials with, for example, our body. So my vision is not only to improve the quality of wearable technology, but actually to look at a new way of improving our interaction with the external world, for example, enhancing it thanks to these devices. And this doesn't need to be thought as, for example, creating ethical issues, because of course that can be designed around a framework of ethics to work with this. However, it's a possibility, it's a new technology that is well exploited, can really gives us a lot of advantage and leverage, for example, towards next challenges that are coming, and we can already see that are coming forward to us. Thank you very much for your time.
Thank you very much, Felice. It's been great to hear your presentation. I would definitely love to have a haptic screen in some way printed on my clothes, especially now when we're all getting a little bit fatigued of our displays.
Yeah.
So there's coming quite a few questions from the audience. I think we have 11 questions, so we'll see how many we can get through now. So the first one is, do you think that electronic wearables will end up like smart watches, as the statistic you shared at the start of the presentation, that people simply stop using them after 6 months?
Well, I think that the problem with the technology, the first generation, let's say, of technology that we have at the moment is really limited in what it can do. Mm-hmm. And indeed, it found an area of commercial application in these gimmicks, as we said at the beginning, type of family of devices, where definitely you can get meaningful information, but sometimes they're not useful information. So if you want to use that spectrum of devices, for example, in hospital setting or in care homes, it's really doubtful that you can really rely constantly on the information those devices give you. And this brings me back to the fact that because you can't reuse them and you can't rely on them for, for very important processes, like I would say key societal aspects, that becomes a big limitation. So I think in general, the fact that people get bored is because there is a limited and doubtfully reliable expectance from those type of devices. Future wearables, if well addressed, actually can be a game changer in this area.
Mm. And I guess it's a bit different putting on a t-shirt compared to putting on a watch or a thing that is quite cumbersome.
The form factor is very important indeed.
Mm. Are you working with fashion designers as well to make your clothes attractive to the consumer?
Well, I mean, you don't want to look only at clothes, because some of these things are not only clothes focused. It's actually, if you're looking at healthcare, fashion becomes less relevant. However, yes, we do. We have interaction with the Royal College of Arts in London. We're also working with clothing companies, clothing industries, and that, yes, why not?
So we had another question coming in saying, can you foresee covert sonic attacks being monitored via wearable biosensors with information sent to secret services?
I'm not sure I really understand the question. So information being captured and shared to secret services?
Yes, exactly, through biosensors.
Through biosensors. Well, I think this is the common issue with big data. I think it doesn't really rely on how data are collected, because biosensors would enable you a new way of collecting data. So you, for example, being able to reliably collect data from your body, which at the moment maybe you can't with wearable devices. But then the way these data are shared, it really depends on how good is the framework shielding these data from actually being shared with unwanted entities. I mean, it could be secret services, it could be anything. So for example, as I said at the end of my talk, a good policy framework and also ethics framework is very important, but this doesn't really need to stop us from developing a technology. As I was telling you the other day, essentially, you can make a good comparison with a knife. Every home has a knife, and it's really an indispensable, a key element in our houses. So everybody uses to cut bread, for example. However, knives can also be a powerful weapon. So it really depends how you use your tool that defines, how good and how indispensable they are. So if you define a good framework how to use it, I can say why not using this new technology.
Fantastic. And we have a question here from Anna Kupani. Could a similar sensor be used for glucose monitoring in diabetic patients, where a quick and finely tuned response is key?
Of course, this is a great question, and it all depends on the sensitivity of the device that you can develop, and on the concentration of glucose in the different media that you are probing. So with skin-based devices, it's very hard, because you will rely only mostly on sweat or moisture from the skin. The concentration is very low. These type of devices also vary, unfortunately, at the moment, their sensitivity according to the position. So it's not really reliable. However, we're working on microneedle type of devices. They can access interstitial fluids, so in the underneath layer of the epidermis. And in that layer, in that region, you actually get a much higher concentration of glucose. And we really think that in the next years, we could actually use a similar technology with improvement on microneedles to achieve that. So we're truly aware of this problem, and we know the way forward.
Fantastic. So it's another one that we should watch this space for the new work coming out. So Ben Lawrence from Kelty says, do we also need better base fabrics and textiles to allow the integration of graphene inks, or are existing textiles suitable?
So we're doing our best to make sure that we develop technology and manufacturing processes that of course can be as much as possible integrated and uptaken by industry. But the problem is that definitely being a completely new technology, you need definitely to think of a way to improve also your substrate or directly your concept of fabric. Indeed, one of the last points that I made is that you can also develop devices on the fiber directly and weave it directly into fabric. So this will become less disruptive to the fabric, but also it would enable to completely change your form factor of your material. You wouldn't be using the textile as a substrate, but you will actually integrate your fiber-based electronic device within the weave of your fabric. So becoming more intimate, with the fabric. And this is very important, I think, as a future step. However, yes, I think there should be an improvement also the substrate, similarly to what happened with, for example, flexible electronics on plastic electronics.
So with this kind of weaving of the electronics into the fabric, we're creating a new type of fabric. Does that mean that the kind of question on washability, where you can only wash it 20 times, completely disappears? Or what would be the kind of consequences of this?
So the 20 times is not a barrier. I mean, the device keeps working after 20 times, but however, what you need to look at is the threshold. There's always a threshold that you don't want to go beyond. And what we saw in our devices so far is that after 20 washing cycles, you go beyond 1% of change of your properties. And this, of course, for electronic device becomes really a tragedy because you would change completely your sensitivity, the electronic response. So you don't want that. However, ISO standards are looking at 25 washing cycles at the moment. So we're not far from the ISO standards. So what I believe is that, with a little bit of improvement, and particularly in working together with industry, the ISO standards can be easily matched, particularly for simple devices like inverters or electrodes. So we're not far from that. The story might be different for fully integrated systems.
Fantastic. And I think we can answer one more question and then we need to move on. So how feasible is the choice of graphene, especially when speaking about mass production?
So we actually tackled this point already. I've been working 12 years in developing really scalable processes. So initially, ultrasonication processes or shear mixing were very low yield type of processes. So they did the job, but not feasible for industry. But we developed a couple of exfoliation processes, one based on the microfluidization that enables to produce, as I said, around 10 liters in a lab setting, of course, about 10 liters per hour. So it's actually at a high concentration, a very high yield process, as well as electrochemical exfoliation that really allows, in a very simple process, to mass produce graphene flakes and also graphene nanoplatelets. So I think the production of graphene per se is not really a barrier at the moment. It might be a barrier for other 2D materials, particularly sourcing, all these new 2D materials that needs to create, of course, a supply chain. And that's a totally different story. But for graphene per se, actually, we already have a lot of graphite in the world. There is a lot of mines already there providing very good quality graphite, and we can already rely on that. So graphene-wise, we're sorted.
I think we'll take one more question, which Ray Shah has asked, and I'm actually wondering about as well. So can these be recycled easily, or is that yet to be established? Because we talk a lot now about hybrid materials and the issue around recyclability. Is this a challenge with these graphene ink textiles?
So looking just at the graphene ink, as I said, since 2015, there's been a lot of studies showing biocompatibility of the graphene, and also with a chemical modification, graphene can be easily dissolved, so becoming really biodegradable. There's been a lot of examples for this, and the graphene flagship, indeed, actually, because it was really aware of this issue, has set up a specific work package tackling this. The problem becomes when you integrate the graphene ink with your textile. In that case, the entire system needs to be biocompatible. We haven't tackled that side because, of course, we rely on what textiles are already available. So ideally, you want to choose actually biocompatible type of textiles. That's why we use cotton, for example, at the moment. which is definitely much more biocompatible. However, the washability tackles a key point, because if you can reuse it, definitely you can remove waste. If you need to dispose of it every time you, for example, do your measurement, like we do, for example, with face masks, with this non-woven type of face mask, that every time you use it, you dispose it off, because that creates a huge waste. So I think if we can improve the washability, definitely it will work towards reduction of waste and so more environmental friendliness.
Fantastic. Thank you so much. Remember that we'll speak to Ola and Felice a bit later as well for the final roundtable discussion, but thank you so much.
Thank you.
It brings up really interesting considerations, especially considering the next speaker, which is Dr. Minh-Son Pham. He's a lecturer in engineering alloys in the Department of Materials at Imperial College London, and he will share how his research is creating a new class of artificial materials, which can make structures responsive, morphing, and even sensing. He leads a group focusing on programmable multifunctional materials, 3D printing, and high-performance metallic alloys for application in aerospace, cars, power generation, and medical devices. I now want to invite Son to share his vision on meta-crystalline materials.
Thank you very much again, Maria, for the nice introduction. And good afternoon, everyone. Good morning, everyone. I hope you have enjoyed fantastic talks by previous speakers. So in this talk, I want to show you the new class of materials called meta-crystalline materials that not only have a very high strength to work in very demanding environments like metals or ceramics, but also have the ability to adapt and evolve like materials created by nature. So the question is, how can we develop such amazing material as we wish? Sorry, I'm trying to move the next slide. Here we go. Yes. So the question is, how can we develop such amazing materials? That's where we can learn from nature. So nature is fantastic in creating materials that can evolve and take all surrounding resources to grow and adapt to the changes in environments. However, most of biological materials, they don't have a high strength like metals or ceramics, as I mentioned before. To work in very extreme conditions, for example, in high temperature, like in rocket engines. So that could be amazing if you have a new class of materials that have high strength to work in very demanding environments, but also have a responsiveness like biological materials. That sounds fiction, but actually that based a lot on science. And before I said further, I want to raise that 5 challenges we want to meet if we want to develop a material that high performing, but also behave like nature. So the first challenge is we need to be able to program the strength as we want. We want to get material to get specific strength, and in particular when they transform, we want them to have a new strength that can meet the new demands. And second challenge is the material is able to store and communicate information within inside them, and if they want to interact with environment, they need to be able to sense and take some action. When they take some action, they need to be able to calculate, computing information, and take some action, including the transformation, morph to different morphology. And when they interact with environment, they need to be able to take feedback and able to self-optimize and learning from their actions as well. And that's the 5 challenges we want to set right in the beginning. So how can we do this? How can we make material with very high performance and ability to evolve and adapt to environments? That's where we can leverage our expertise and knowledge in 2 very different approaches. One is our dream in developing invisibility cloaking materials to make an object invisible to the light. Another is a secret also found in the way we develop high strength alloys, like in aero engines. Now, look at our dream. We want to wear a cloak that can make us invisible to the light. So now if you look the way why an object is visible to the light, if you shed a light to an object, the object will reflect the light, and by doing that, the object is visible to the light. Now, if you cover the object by a cloak, and if assume we have ability to engineer the building block inside the cloak at the length scale of nanometer with the same length as the wavelength of the light, and that building block, if you arrange them in a clever way, they will interact with the light and guide the light go around the object, and by doing that, they will make objects invisible to the light. And that's the important thing. You need to be able, we need to be able to tailor the building block. And if you can able to do that, you can get the functionality we want, including the programmability. And that secret also shared in the way we develop high-performing metals and ceramics. If you look at any piece of metal, for instance, you take that from aero engine and have a powerful microscope, you could see inside a metal would have many grains of crystals. That's what you see in this micrograph here to show us different colors represent for different grains. And the length of the size of the grain is almost the same size as the diameter of our human hair strand. And inside each grain, that consists of billions of atoms, and atoms arranged in very ordered ways. That's called crystal lattice. First, what you see here is one example of crystal lattice. Atoms located at the corner and the side face of a cube. And the arrangement of atoms, in most times, is still the same. However, the way they're oriented in space is different when we cross from one grain to the other grain. So that arrangement of building block governs the strength of the alloys and ceramics. And that's the secret. Now, if you want to understand further, now just take a piece of single crystal and you stretch them and you measure how much stress you need to pull them apart and how much extension they can bear before they fail. So that is the extension is represented by strain, and the force, how much force or stress is on the y-axis here. And in the beginning, you see the relationship between stress and strain is linear. It's similar like when you stretch a spring. Beyond a certain point, that's called yield point, you see the internal defect inside the crystal start to move, and that causes the loss in strength. So you see the drop in strength, and that happens repeatedly. That leads to very unstable deformation behavior, but also low strength as well. However, if you have the same specimen, but that made by an aggregate of crystals, you see the behavior now so much different. You have a higher strength, and the material become stronger and stronger during the deformation. And the collection of grains that lead to the higher strength, that's one of the key principal strengthening mechanisms in developing high strength alloy. That provides us ability to design any strength we want. And that is what we are doing at Imperial College. My research group, guided by the science of metals and also other materials classes as well. And we combine with advances in manufacturing, in particular 3D printing, and in other words, commonly known as additive manufacturing as well. And by learning from the way our dream to develop invisibility cloak materials, we understand if we are able to design a building block and we arrange the building block in novel way, we can get an artificial crystals that are lightweight because we extract most of the material away, and we can achieve the strength we want. And also with the way we manipulate the building block, we can make materials smarter as well. So here, as I said in the beginning, we need to achieve, or we need to meet the five or address the five challenges. The first challenge is ability to program the strength, and that's where we learn from the strengthening mechanisms in developing high-performing alloys. In here, we design a building block, and we mimic or we create artificial single crystal, and the behavior of single crystal is very much similar to the behavior of the real natural single crystal. And we also see a drop in strength and unstable deformation behavior. When we created an artificial polygrain crystals, you see the deformation behavior now is much stable, and we can get higher strength. And that really depends on the way we arrange the building block inside the artificial crystal. We can get even higher strength if we want. So we can program the strength we want. And that's the way we can meet the first challenge. The second challenge, as I mentioned, is the material needs to be able to store information and communicate information inside them. So that is the way we go back to the way we designed the building block, and we arranged the building block in 3D space. First, in this video, you see we created artificial polygrain crystals, and we arranged them to specific location, and with that we can embed information. We can dictate how the material behaves under the compression, and they deform in a specific way as we designed. And the important thing is, with the way we arrange the building block, we can ask them to communicate in given way, and with that we can broaden our definition of invisibility. So for example, if you have an impact force impact on this material, and with the way we design the building block, arrange them, we can direct the force, we can make the force transferred and directed inside material along specific way, and we can avoid certain location to make that location invisible to the force, so that can improve our protection in case we want to protect any object inside the material. And that's the way we can tackle the second challenge. The third challenge, as I say, if you want to make material evolve, they need to understand how the environment, the surrounding changes, and that means material can sense, and then they can take action. Certainly, we can use the sensor. We can embed sensor or actuator inside material. But the more clever way is we can use the functional materials to fabricate our artificial crystals. First of all, in this video, you can see a material that can sense the changes in the external magnetic field. The reason for that is because people aligned the micromagnet inside this 6-leg material in specific way, and when we manipulate the external magnetic field, the legs can respond in different way, and with that the material can wrap around a medical pill and rolling and go to the site of delivery and then release the pill. And with that, material can behave like a robot. So that would be fantastic, because we do not need to use any actuator or motor, or do not need to provide any like electricity to the material. And the fourth challenge is also material able to compute and sensing and take some evolution, like a transformation or morphing. So that also where we can learn from crystals as well, from nature. So one class of crystals is called the shape memory alloys. They have a fantastic functionality. They can have a two-way morphing when we heat it up and when they cool down. First of all, in this video, show us about the artificial metallic flower that can open when we heat it up and closes when we cool it down. The reason for that is lie deep down inside the shape memory alloys. The shape memory alloy have two crystal structures. One is called austenite, that only present at high temperature, and another crystal phase is called martensite, present at room temperature. So when you deform martensite at room temperature, it changes the shape, and now if you want to return the original shape, we first need to heat it up, and the deformed martensite we transform to austenite, and when you cool it down, it will transform back to the original undeformed martensite. And by doing that, the shape memory alloy able to recall the original shape. That's fantastic phenomenon we see at atomic scale. Now, how can we translate that knowledge and that phenomenon from atomic scale to millimeter or even meter scale? That's where my research group at Imperial play a role here. We use advanced computer software to design an unit cell, and that utilizes a phenomenon in structure called buckling, and we able to transform back and forth between two stable configurations, and with each configuration they have a specific strength, and we arrange that building block in 3D space to create an artificial crystals able to transform back and forth depends on the loading conditions. And this material, you can see we remove most of solid material inside so that the artificial crystal is very light and with a specific strength as we design. And you can see that can open a variety of applications, for example, in transportation. Now we are facing global challenge in reducing the CO2 emissions. And with that, one way to tackle that is to reduce the weight of vehicles, and by doing that, we can increase the fuel efficiency and reduce the CO2 emissions. Now, if you apply that kind of artificial crystals inside cars, in particular in front of cars, we have a crumble zone, and the impact energy can activate the transformation from one configuration to the other configuration. The material can absorb energy, protect the passenger and the driver inside, while after the impact, the material can recall the original shape, and with that we can reduce the cost of repairing, for example. And the morphing also and evolving materials can also open opportunities in improving the well-being of our society. For example, here's one application we are working with children is to develop adaptive artificial hip. Hip can evolve and behave like a natural bones. So one problem with artificial hip is they cause stress shielding, and that means that inhibits the regrowth of our own natural bones, and that means it will degrade. I mean, the bone of the patient will degrade over time. If we want to promote the regeneration of the bone, we really need to design our artificial hip become less stiff, or in other words, it's more compliant. And with the way we can tailor the stiffness by arranging the building block, and the artificial hip can evolve thanks to morphing, in particular with the evolution, regrowth of our natural bone. And hopefully after over a few years, the natural bone will regrow and the artificial hip disappears, and the patients can have their own bone back. So that is going to be open quite a lot of promising future. And the ability to develop morphing and sensing and responsive material could open also opportunities in other applications as well. So one of that is to develop more resilient infrastructure. So we can design shelters that can transform, change in different morphology in response to natural disasters. For example, in flood situation, for example, the shelter can self-elevating to protect the people inside the shelter. But also when we downscale that, or even upscale, we can design robotic flying vehicles, like drones. They can fly and behave like a bird, for example. And as I showed you before, ability to absorb energy and redistribute energy as we want, that will help us to improve the protection of our personal protection device, for example, the helmet. That is in 5 years. And if we think a little bit further, in 10 or 15 years, go back to our dream to develop invisibility cloak materials. Now, as I mentioned before, we can broaden the definition of invisibility. We can make an object invisible to different signals that could be acoustic wave or seismic or elastic mechanical wave. We can use material in our city to minimize the noise pollution we can make city more quiet. That will improve the well-being of people in the city. But also, when we can make a materials that become invisible to more energy wave, like a seismic wave, we can protect an important area. We can deflect the seismic wave away from important areas, for example, cities or important buildings, for example, like a nuclear power plant in case of earthquake, for example. And with advances in nanofabrication, we can go back to our dream to develop invisibility cloaking materials that are invisible to the light, and that really where we need to engineer and tailor the building block at nanoscale. And that is the roadmap for the future, in particular with the foundation I present in the previous slides. So we develop artificial crystals with high strength and lightweight and ability to adapt. So we see that's why variety of application in transportation, and increase the resilience of our infrastructure to natural disasters as well. So in 15 and 20 years, by 2040, we can integrate all functionality. I will show you that's very possible to use what we have learned so far, inspired by nature. We can develop intelligent materials that can learn and respond better to the surroundings. And that would help us to improve the health of our society, the well-being of our society, and the future which will become more autonomous, that help us to explore in the different world, different areas where human could not easy to access, or the area where it's very dangerous and unhealthy to the human. We can send material behave like a robot, help us to build a satellite, or help us to explore different locations, different worlds. And that is my vision in 2040. By learning from nature, we can design material that can adapt to the environment, can compute and sense and learn. And by doing that, they become smarter and more intelligent, help us to better to adapt with the change in the future. And with that, I want to thank you for your attention, and we'll be happy to answer any questions.
Thank you so much, Son. It was extremely interesting to hear how you're creating a new class of materials that almost become like living and can help us address things like climate change and health care. I think we can see that there are loads of applications, really interesting future applications. So I had a couple of questions. So first, shape memory materials have been around for a long time. So what has really enabled this step change to happen?
Yeah, thank you, Maria. That's a very nice question. I do agree that shape memory alloys already present for a long time, but that's based on the intrinsic phenomenon at nanoscale or atomic scale. And the novelty of our approach is we can enable the transformation at millimeter and centimeter scale, and it doesn't need to have an intrinsic shape memory alloys. We can apply this approach to any kind of other materials, and actually we use just normal polymers, it's normal metals, and enable the transformation. So we can upscale to larger infrastructure buildings, for example, and we can enable the transformation with the available resources. Do not need to use fancy shape memory alloys.
Fantastic. And I think this follows on one of the questions for the audience that came in during your talk, which is how applicable is it as a construction material? Can you use it today as a construction material? Yeah.
So that's very much, we just use the normal materials, just normal metals, and also, like a scaffolding structures, more stick model, and we can enable the transformation. Recently, we need to do a more clever way, because we need to build the right building block and then arrange them in specific way. And with the normal, existing construction materials, we might need to embed some kind of activator, because they they don't have like a magnetism or shape memory functionality of the intrinsic materials.
So what is the largest structure that you have enabled this material to work in so far?
Oh, that's a very good question. That very much is limited by our capacity in fabrication. So because we use 3D printing to fabricate our design, so basically that's the bio volume of our printer is our limit. But with the advances in manufacturing, where people can use robotic arms, they can increase the scale of the build volume. That we can upscale larger. But also you can see people already apply like artificial crystals already, even they are not aware of like a scaffolding structures, for example. It's a very simple form of artificial crystal, single crystal.
Fantastic. And a question here from Emily Wheel. There are so many exciting applications for this. What do you think might be the most promising opportunity for this technology early on?
Yeah, that's also a very good question as well. The future is quite promising, and because we not rely on the properties of the intrinsic materials, we can apply the approach to any kind of materials and particularly in structural applications. So in the near future, I think the most promising could be in transportation, because we have a strong demand in reducing the weight, and not when we reduce the weight, we need to think about it still need to have a strength as we use heavier materials, and also ability to absorb more energy to make the passengers and the drivers safer. So that is in near-term future, I think, in transportation. But also a little bit further could be in the healthcare application, because we can make artificial like a hip or some other device can able to transform. So actually, we are working with a group of surgeons in Hammersmith to design transforming catheter, help us to manipulate the catheter tip to perform some surgery inside patient's body.
Fantastic. So Ben Lawrence has a quite good question here. And so 2 years ago at the Tech Foresight conference, we had Dr. Conor Mayan speaking about 4D printed polymer material. How much of a crossover between these polymers is there between these polymers and these meta-crystalline materials?
Yeah, thanks. That's fantastic questions. Certainly, we have some overlapping between 4D, 3D printing and this approach. But 4D, 3D printing more focus on manufacturing, and we focus on design of material, and we use 3D printing to realize our design. So that's the common is we use 3D printing to realize our design. But actually, if we have another manufacturing route, we can fabricate the design we want. We do not need to use 3D printing. So actually, we buy a lot of like rods, and we arrange them, we bond them together either with welding or just use them not to bond them together. And with that, we also get able to realize our design. And with 4D printing, you still need to use the functional materials. Material need to evolve because 3D printing could not make material evolve. That makes, and this one, I mean, our approach is different. Most of the case, we do not need to use fancy materials. We can use normal materials and make them evolve.
And I guess the cost goes down as well.
Yeah. I mean, if you think about the cost for chip memory alloys, it's very expensive compared to other alloys, other metals. Now, if you do not need to use chip memory alloys, use just normal metals, which is much cheaper. And fabrication also easier, because to fabricate chip memory alloys, we need to control the chemical composition very carefully, because of the range they have of the chip memory functionalities is very narrow. Anything out of that range, the material lost its functionality.
I think it's quite interesting, because I remember in that talk, we were talking about the two-way morphing, and that was more of a dream of being able to do something like two-way morphing, which you can already do with your class of materials that you've developed with your group.
Yeah, that's absolutely. Just we need to combine our expertise in different disciplines, from structures, from mechanics, materials, and also art as well. So actually, we learn a lot from art, I mean, kinetic sculpture that enable the sculpture behave like a living animal. So that's where we learn from.
Fantastic. I think we'll do one question and then we'll move on to a very, very short roundtable conversation, as we don't have, we're running a little bit behind. So the last question is from Nick Rimmer, where he asks, are there other manufacturing techniques that could be used rather than 3D printing? And I think you actually sort of have answered this already.
Yeah. Now we're buying a lot of kind of wires of metals, and then we just weaving the way we can bond them together. So no need to be kind of physical bond, like a welding to join them together, but also we can use knot, for example, or just the way we weave, they spot the other and they can form a building block in regular way. Certainly there's a limitation with that, because with 3D printing we can make much more complex. But depends on application, and also depends on the constraints in finance. We can use just normal, existing manufacturing approach to fabricate the design.
Fantastic. Thank you so much, Son. It's really interesting to hear about your work and the potential application. So it's now time for the roundtable discussion, and I want to welcome back the two other speakers, so Ola and Felice, and we'll have time for 2 very short questions. I'll ask the first one, and then if anyone from the audience has a question that they really want to have answered, this is the time. Welcome back. So we've received a lot of questions this session, but to begin with, we've talked about different materials and the changes of the structure to these and the development process. So what might be some of the changes to the design or engineering process that emerge from the new materials that you're proposing? So what could this mean in terms of the process of development, essentially? Felice, would you like to start?
Yes, the process, in our case specifically, being new materials, the synthesis process is totally new. So essentially we really had to, of course you rely on existing techniques, but you really need to reshape them in order to achieve what you really want to have. And specifically for 2D materials, it's critical to achieve that aspect ratio of having them essentially confined or atomically thin on one direction, while keeping, the macroscopic X and Y direction, so this kind of planar. So this has been really challenging, of course, over the last decade since graphene started. However, you want them to align this processing with existing industrial processes, make sure that somehow the technology transfer is really facilitated. So in any case, it's really a game of essentially developing the best technique that is, however, transferable and somehow essentially doesn't require huge investment from industry. And that's what we've been doing really over the last decade, trying to understand and facilitate the technology transfer. For what concerns, I think, in the broader view of stretchable and malleable materials, I think in general, for what I can see in the textile area and the stretchable electronics area, I think particularly for stretchable electronics, there isn't really a lot of, I would say, standard procedures. There's a very open field to essentially adapt the technique that are already there or that somehow are still lab-based to a new technology or new material like 2D materials. For what concerns instead textiles, is a very solid technology. There are already very solid standards. It also has not dramatically evolved actually over the last 100 years. I mean, textiles more or less are manufactured in the same way they were manufactured 100 years ago. So from this point of view, introducing new materials might be a more disruptive input. Therefore, I think we need to be a bit more cautious there when we introduce that.
That's really interesting. So quite disruptive for the current industry of textiles, essentially. I think, Ola, you already mentioned some of the kind of learnings to keep in mind as you're processing, as you're developing new batteries. Is there anything else that you think would be interesting to share with the audience today?
So for our technology that we're trying to commercialize at the moment, the idea is that we are not replacing the entire system, but it seems that we're introducing some improvements to the system, and actually the industrial partners are willing to meet us halfway and improve other stages of the process, and they see the benefit of it. So in a way, we do influence the rest of the process. So that's really, really interesting. So that's earlier stages of the material that we're getting for recycling. But then at the end of the process, we also create new materials that typically battery manufacturers are doing themselves. And again, similar to textile industry, lead acid recycling industry is pretty established, and they're used to do things for many years in the same way. So it's also interesting how this develops, and talking to people and listening their opinions and learning from them and sharing information. That's quite exciting.
And for you, Son, because does this, I mean, you're proposing a material that can do things that other materials can't. So there needs to almost be a different approach to the kind of engineering, almost process behind putting this into things, right?
Yeah, absolutely right, Maria. However, I want to point out we utilize existing materials, existing processes. The only thing we ask engineers or users is to think their imagination, become creative and ingenuity. And that's the key thing, because I mean, if you see, that is, we just design building block and we arrange them in novel way to enable the functionality we want. And we can apply it, really try it, I mean, with some design, we test with the metals. I mean, we fabricate by metals, polymers, and certainly we haven't tried with ceramics. So, but I would expect we have the same functionalities. Certainly, I mean, there's a limitation if we use certain kind of materials, they behave differently. So that also leads to very interesting phenomena. For example, if you use metals, inside metal, they have crystals itself. And at larger scale, we have artificial crystals. They mimic the other, that little kind of fractal hierarchical structures. And the phenomena is scientifically, it's very interesting. So it's not only about the application point of view, but also lead to open a new area of research. So yeah, for my research directors, it's the main thing we ask engineers and users to just need to rethink the way they design and be creative and also based on science and nature.
Fantastic. I think that sort of goes along all the speakers today around using the imagination and being really creative about where these new processes and new materials could be placed. So we have one last question for the audience, which will be the last question for today. So it is, what do you think would be the single biggest boost that could help you as a researcher and startup companies to reach your 2040 goals other than financial? Is it technological, social, political, I'll add creative, or something else? Anyone would like to start? Ola, would you like to start?
Yeah, I'm happy to go. I would love it to be a social awakening when we all start thinking and we actually learn something from the crisis we're going through, and we rethink how we approach the climate change and how that there will be some good lessons coming from it. So definitely, if it could be social, it will be going in the good direction.
Fantastic. What about you, Son?
Yeah, I do agree with Ola. We need to think about our impact on social, but also environment as well. So we need to have a goal. I mean, say in 40, which challenges we want to solve. Let's say in environmental effects, and we need to understand. I mean, to learn from nature, but also we need to have a good fundamental knowledge, because our design just based on what we learned from science of metal. And certainly with others at the time, advent of the manufacturing, that's the right time for us as well. But we can learn a lot from existing knowledge, and with a good might want to solve something in 20 years, that hope, and we put effort into that, and we can achieve some meaningful impact.
So Felice, you get to go last. Sorry.
Yeah, no, I definitely align with them. I mean, the social changes will provide also a meaning for more funding, because if there is a social understanding, of course, it will follow even politically or strategically to enhance or increase the number of the amount of funding in general for research and technology. I would say that normally is a game of different parts. I mean, technology also plays a huge role there. And for example, if we didn't have these, in my case, new materials or this novel 2D material, I wouldn't be here talking about this. So I think it's also, you know, it plays different roles. Social is so strongly linked to funding, and we need money. And definitely, you know, cut to budgets in this case would be really disruptive, negatively disruptive. But technology plays a huge role as well to supporting us.
Fantastic. Thank you all speakers. I think that's a really nice way to end this 2 hours and a little bit session today on malleable matter. So we've heard visionary perspectives from material innovation experts and startups about the future of their field. And now it's really time for the thanks. This is the last of the 3 sessions encompassing TF 2040 for this year. And I want to first thank our fantastic speakers. Thank you, Dr. Ola Hekselman, Dr. Felice Torrisi, Dr. Minh-Son Pham. You have given us incredible insight about how we can approach the question of malleable matter and how they can actually create these innovations for good